Okay, hello everyone. Welcome back to another one of these tutorial videos for the theory of representation. So in this video, we'll be looking at how to use the public limit for context-free languages to show that a language is not context-free. So the way this works is it's very similar to the public limit for regular languages. So for context-free languages, we have a similar public limit, which says something like if L is context free, then L satisfies some pumping limit conditions. Okay. So then this is a necessary condition for L to be context free. And so we can use necessary conditions to show that something is not context free because we can say, well, if L does not satisfy the pumping limit conditions, right? So if we use the contrapositive, so this is the direct statement. Now, if we take the contrapositive, we have that L does not satisfy the pumping limit conditions. Implies, so what does this imply? This implies that L is not context free. Okay, so I'm just going to write down the contrapositive statement directly. In the regular language video, I actually give you the non-negated statement. Here, just for the sake of brevity, I'm just going to give you what uh, the contrapositive statement is. So the contrapositive statement is if for every natural number n, or every natural number p strictly greater than 0, there exists some string L with length at least p. Then we have that now we have a decomposition, but now it's not just XYZ, it's UV XYZ. So for every UV string UV XYZ in sigma star. So I'm not quite sure. I think it might be slightly different in the slides, but you can use whatever sort of letters you want as long as it's consistent in the statement. So for every possible decomposition of the string W into 5 pieces, right, where the middle pieces, so VXY, the length of the middle pieces is at most P, and the length of this piece and this piece together is at least 1. So in other words, Vy is strictly greater than 0. Then there exists some natural number I, so that's the pump, where Wi, we shall define similarly to the one for, so the statement for the regular languages, U, V, I, X, Y, I, Z is not in L, right? So this resulting sort of pump, right? So notice here I'm pumping both V, right, I times, and Y, I times, and the same number of times, right? So if this is true for every single decomposition, so now what we're going to see is going to happen is we have to, this sort of, the effect of having 5 substrings means that now we need to consider cases for the decomposition. Okay. So for every single case, what we need to show is that there exists a pump. It could be different, right? For each case, you could have a different I. It's very possible. And so for each pump, you have to show that the resulting Wi is not in L, right? So you have to show that there's at least one pump where this is true, right? And so if that's true for all cases, then suppose L is some subset of sigma star, then L is not context free. Okay, so that's the statement of the puppet lemma, the contrapositive statement for the puppet lemma for context free languages. And so now what we're going to do is we're going to use it to show that this language here, which let me just copy this language here, which is the language um, containing strings of the form A, B, C, where the number of C's is strictly greater than the number of B's, which is strictly greater than the number of A's, is not context free. Okay. So in this video, we're just going to prove that some language is not context free. But in the tutorial next week, part of the things I'm going to be doing is giving you tricks in determining sort of if I just give you a language and I ask you to classify it in terms of regular, not regular context free, not context free, what are some general guidelines to do that? Okay. But for this video, it's a bit, well, yeah, it's a bit easier because I'm just telling you sort of to use the proof technique. Okay. So how am I going to do this? Again, let's just play a game, right? So this is going to be the same strategy where I play the existential quantifier, right? So my term is always going to be the existential quantifier, and my opponent's term is going to be the for all, right? And the point of the game is for me to win, right? So I need to, in every single sort of um, way that the for all player picks um, the decomposition W, I have to find a way to defeat the for all player by finding a pump. Okay, so let's do that. So the for all player starts, and so let's just say my opponent picks the natural number P in N, where P is strictly greater than 0. Right, so I don't know what P is exactly, right? So a very common error, which is very, very wrong. Please don't do this in the assignment or in the midterm. A common error is to pick a particular P, right? This is extremely wrong because maybe you defeat the opponent for, P17, but, you can't force the opponent to pick P17. That would be forcing the opponent's hand. So you need to assume that the opponent chooses an arbitrary P, and you have to work a strategy that works for NP. Okay. So now it's my turn, right? It's the existential quantifier's turn. And so now I need to pick some string in L where the length of that string is greater or equal to P. So it can't, right? It obviously can't be like the standard string that people pick is, AP, BP, CP. That you can use to show that A and B and CN is not context free, but that's not going to work here just because the string, to begin with is not in L. So one pretty safe choice when you have strict inequalities is just to make the sort of the greater side, right? So in this case, the number of B's just have one extra versus the thing you're actually comparing to. Okay, that ends up being like relatively simple, a relatively safe choice because then when you pump, you know that the string you're pumping has to have at least one length, at least one. So when you pump, you know that you're at least going to get sort of if here I pump down and I have only one extra B versus A, then when I pump down, I might get the same number of A's and B's, and that already sort of breaks the language definition. So one like good starting choice for W is when you have an inequality is to sort of just choose to have something like in this case AP BP plus 1, and then because the number of C's has to be strictly greater than the number of B's, then let's just say it has one extra C. Okay. So this is like a good starting choice, even if you don't exactly know how the game is going to play out. You can start with this, and if you see you get stuck, then you can sort of backtrack and see if you can slightly change your choice for W. Okay. And so this is definitely an L, right? It respects the definition because, P plus 1 is strictly greater than P. or p plus 2 is strictly greater than p plus 1. And the length of W is 3p plus 3, which is definitely greater or equal to p. Okay, cool. So now is the interesting bit, right? Now is the interesting bit where it's back to my opponent's turn, right? It's back to my opponent's turn. And they sort of decompose the string into UV, X, Y, Z, right? So this is when it gets important to be a bit more careful and to sort of explicitly write out the string like so. So I have p plus 1, and then p plus 2. Okay. And now I'm going to consider cases based on where the VXY part of the decomposition can be. So there's going to be a few cases. The first ones that are going to be sort of immediate to deal with are going to be when VXY, that's all in A's, and VXY, that's all in B's, and also VXY, that's all in C's. Okay. So I already have 3 cases. Case 1, case 2, and then case 3. So typically the rule is, well, let's start with case 1, and let's see if case 1 and cases 2 and 3 end up being very similar, then we typically are allowed to just do case 1, and just say that cases 2 and 3 are going to be the same as case 1. But let's first see how case 1 plays out, right? So case 1 is the V's and the Y's are within the A's. So that means that, V can be represented as A power K1 and Y can be represented as A power K2, where the sum of K1 and K2 is at least 1 and it's at most P. It's at most P because VXY is at most P. And this is at least 1 because, so this goes with this and this because VY is strictly greater than 2. Okay. So now, right now, what can sort of happen if I have my A's all in here? Well, remember what I need to do now is for this particular case, I have to be able to pick a pump where when I pump the V's and Y's, I get a string that's not in it. So here, hopefully, it's relatively easy to see that if I inject an extra Y and V here, right, then I'm going to add an extra K1 plus K2 A's, right? So then I'll have P plus K1 plus K2 A's, and that's definitely going to be at least as big as P plus 1, okay, because K1 plus K2 is at least 1. So it looks like, right, that's telling me that I probably need to pick a pump I is equal to 2, right? Because I need to, so now this is like the existential, so the existential case, or the existential move is now sort of embedded within this case 1. So I need to pick an I such that WI, which, remember is U, VI, X, YI, Z. This is U, and then I number V's, and then X, and then I number Y's, and then Z. Okay, and I want to show that this is not an L. So, right, like I said, if I pick I is equal to 2, then I'll get W2, and then W2 is going to be, injecting an extra V here and an extra Y here, but that's all within just A's, right? So if that's all within just A's, then that means I'll get W2 is going to be AP, right? So the initial P's that are in here, plus an extra number of A's in BY, right? So that's plus K1 plus K2, and then B, P plus 1, right? These remain unchanged. And this is not, right? This is not an L, right? Why? Because the number of A's in W2 is P plus K1 plus K2. And then K1 plus K2, this is at least one. So then this is greater or equal to P plus one, right? And that's already sort of a break in the definition of L, because the definition of L tells me that the number of A's must be strictly less than J, right? If it was less than or equal, then I would probably need to pump, uh, with I is equal to 3 or more, right? Because then I would get um, a strictly greater than number of A's in that case, okay? So that completes case one. Now, if I look at case two, um, one way of doing case two is, you have the V's and the Y's within the B's. And then I pump up again just by one. So I set I is equal to 2 here. Then I get P plus 1 plus K1 plus K2. And this is at least 1. So then this together is at least 2. So then I have that the number of B's is greater or equal to the number of C's. Again, that breaks the definition. So because that case is exactly the same as case one, I can just say that case two, I'll just say that case two is just same as case one. Now, what about case three? Is case three the same as case one? Well, now the V and the Y are in the C's. So now if I pump up, right, if I set I is equal to 2, then I have something like P plus 2 plus K1 plus K2. But then this is still strictly greater than P plus 1, right? Because I'm just adding more C's. So that's not going to work, right? So that tells me that case three is actually different from case one. I need to use a different strategy. Namely, I have to pump down, right? So case three, that's going to be when the V's are equal to CK1 and the Y's are equal to CK2, where K1 plus K2 is less than or equal to P, greater or equal to 1. And so here, right here, I need to pick W, I need to pick I is equal to 0, because then if I is equal to 0, then W0 is just X. No, sorry, not X, is U X Z, right? So I deleted V and Y. So I removed K plus one, K sub K1 plus K2 C's, meaning that, right, meaning that I have AP, B, P plus one, C, P plus two, minus K1 plus K2. But then this is not an L because P plus 2 minus K1 plus K2. This is, right, so K1 plus K2, this is at least 1, right? So that tells me that this is at most, right? This is at most P plus 2 minus 1, right? Which is just P plus 1, right? So then I have that the number of C's, right? I have that the number of C's is strictly less than or equal to the number of B's, okay? And that again defies the definition of my language L, right? And so that gives me a way to defeat my opponent for case three. So that's why I couldn't say that case one and case three are the same. Like I can say just the same logic because that's not true, right? In one, I had to pump up, and in another, I had to pump down. I noticed though an extra note. Notice that for case two, I could have also, in that case, pumped down, because then I would have gotten something like the number of p's is greater or equal to p plus one minus k1 plus k2, right? Okay. Okay, but we're not done yet, right? So these were three cases. But hopefully you see that there's still a few more cases to do, right? So let's copy this guy to back here. Okay. So what are the other cases, right? Imagine you're sort of moving this VXY block through the string, right? So where can you get differences in cases, right? So another sort of difference in case is you're moving the VXY from left to right, and now the X happens to straddle the border between A's and B's. And then the V is on the left and the Y is on the right, right? So that's one case, right? So I have X in the middle, V on the left, Y on the right. So that's case 4. Then there's the same thing, but for BCs, right? So I have X and Y. I have X is straddles B's and C's, and I have V and then Y on the left and the right, respectively. So that's case 5. And then I have that X straddles, X could straddle from A through the B's all the way to the C's. And then I have V on the left and Y on the right. Hopefully you see that that's actually not a case, right? So this is actually, what's going on there? Okay. Hopefully you see that that's actually not a case, right? So this case 6 is not a case, not a valid case. Why? Because then the number of x's, the length of x would be equal to p plus 1, right? But I have a restriction. I have a restriction that the length of vxy is at most p, right? So this is a contradiction, right? This is a contradiction. So that's why this 6th case is not valid. So the only possibility is that I have v on the a's and y on the b's, and then v on the b's and then y on the c's, right? So then let's consider each of these cases. Let's start with case 4. If it seems like case 5 is the same as case 4, we could just say, it's the same and move on. If it's different, then we have to do both cases individually. So let's look at case 4, right? In case 4, we have that the V's are, let's say, K1As, and the Y's are, let's say, K2B's, right? So now I need to find where, let's just specify where K1 plus K2 is between 1 and P. And notice actually now there's an additional restriction, right? There's an additional restriction on the K1s and on the K2s. It's that K1 is at least 1 and K2 is also at least 1. Why is this the case, right? Why? Because I'm saying that V is sort of a non-empty string with an A, and Y is a non-empty string within the B's, right? So the other way of looking at it is if K1 or if K2 was actually 0, then it would just be that this was back to case 1, right? Because if K2, right, so if the Y was within the B's, but it was actually empty, then you just have case 1 where you only have that the string you can pump is within the A's. So then you just use the same strategy and pump up, but like it's the same as case 1. So we're just not going to consider that. Like we don't lose any generality by just saying that K1 and K2 are at least 1, because in either case, if they're 0, we've already sort of dealt with those cases. Okay. So that's the additional restriction. So really, actually, technically speaking, this is really K1 plus K2 is greater or equal to 2, but I mean, this is still, yeah. So technically speaking, K1 plus K2 is greater or equal to 2 because of this restriction. Okay. So then, what does that mean in terms of how I'm supposed to pump, right? So if I look at my string, I have part of my string is in within the A's and part of my string is within the B's. So if I pump down, right? If I pump down, so I'll get something like minus P minus K1, and here um, P plus 1 minus K2. Imagine K1 and K2 is equal, right? That's very possible. Then if K1 and K2 is equal, the difference between the number of A's and B's stays the same, right? There's still going to be the fact that the number of B's is strictly greater than the number of A's. And it's not going to change anything in the inequality between the number of B's and the number of C's, right? The number of C's, if you pump this down, right, is still going to be strictly superior or greater to the number of B's. Okay, so pumping down is not going to work. Now, what about pumping up? So if I pump up, it's still possible that K1 and K2 is equal to they're equal, right? In which case I don't have a contradiction there, but I will have a contradiction in that the number of B's is going to be greater or equal to the number of C's, right? Because now I have a guarantee that K2 is greater or equal to 1. Okay. Remember, I didn't have that guarantee before, but in this case I do. So that guarantee being that both of these two things were greater or equal to 1. And so it seems like what I do need to do then is to pump up. So here the existential, right? So the existential, that was the remove here, just to label things. Okay, so again, it's going to be the existential term, but within case 4 now. And so the existential modifier, so you, us, we are going to make I is equal to 2. And then for I is equal to 2, I get, W2 is V2 X, Y2, Z. And in that case, this is going to be A power P plus K1, B power P plus 1 plus K2, and then C power P plus 2, right? And this is not going to be an L. Why? Because now P plus 1 plus K2, because this is greater or equal to 1, this is greater or equal to P plus 2, right? And so that's sort of a contradiction with the definition with the necessary and sufficient conditions of my language, because those say that the number of C's, right? The number of C's have to be strictly greater than the number of B's, right? So here that's not the case. I have a sort of a greater than or equal to on the number of B's. So that's not an L, and so that sort of covers, or that defeats my opponent for case 4. Now, what about case 5? Let's see if the logic is the same. So in case 5, right? In case 5, if I pump up, then I get plus K1 plus K2. Then if K1 is equal to K2, the difference here still remains 1, right? And here I have a strictly greater number of B's than A's, right? So, and like notice, I'm not saying that K1 is always going to equal K2, but it's possible that my opponent, right, is trying to be cheeky and they say, well, I'm going to choose K1 is equal to K2. That's possible. I can't control for that possibility. And so if they do that, then if I pump up, right, if I pump up, then I'm not going to get a contradiction because I'm still going to have this sort of inequality like this. Okay, so instead that tells me that I have to pump down, right? Because if I pump down, even if these two things are equal, P plus 1 minus K1 is going to be less than or equal to P, right? Because K1 is at least 1. So, so that tells me that case 5 is not the same as case 4, and I do actually have to write it down. Okay, so V is EK1, Y is CK2, where let's actually write the correct or like the more correct inequality, where I have this and I have this. Okay. And now what I said is I'm going to pump down, right? So I pump down. So then I have W0 is U V0 X Y0 Z. So that's just U X Z. And so the result of that is, the number of B's remains untouched. Um, number of A's, sorry, the number of A's remains untouched. The number of B's, however, goes down, and the number of C's also go down. So I can't do anything about the inequality between P and C, B and C, but I can say something. I can do something about the inequality between the number of A's and the number of B's. Namely that, in this case, P plus 1 minus K1, because K1 is at least 1, then P plus 1 minus K1, that's at most P plus 1 minus 1. So in other words, P. And so that means that the um, the number of B's, right? The number of B's is at most the number of A's, right? So I sort of, my inequality has become flipped. So now I have a contradiction, right? I have that this guy is not in L because of the reason I just stated here. Okay. Okay, so that's case 5. Now, are we done? No, right? We're not done because we haven't considered that this V could be the one to straddle the A's and B's, right? That's entirely possible. So, and the same thing for the Y's, for Y straddling A's and B's, and the same thing for B's and C's, right? So we have to account for that, those cases as well. So let's do that here. Okay, so let's erase most of this. How do I delete? Delete, okay. Right, so I have a few more cases. I have where B straddles, or Y could also straddle the A's and B's. V could straddle the B's and C's. Or, sorry, it could be Y. Y could straddle. Y could straddle the B's and C's. Okay, so then I have 4 more cases. So this is case 6, 7, 8, 9. Now, this seems like a lot of cases. You're going to see that this is always my favorite case because the argument is very nice and elegant and it covers a lot of the remaining cases. So for case 6, what's going on here? Well, for case 6, I have something like the V's are some number of A's and then some number of B's. Let's just say K1A's and K2B's. And Y is some additional number of B's, let's say K3. So what do I know about K1, K2, K3? I at least know, right? I know that together their length is greater or equal to 1 and it's at most P. Now, what do I also know, right? I also know that K1 and K2 cannot be 0, right? Because if K1 is 0, right, so then this thing is not here, then the V's and the Y's are both just B's, and that's just case 2, right? What if K2 is 0, then V is A's and the Y is B's, then that's case 4. And I've already sort of dealt with cases 1 and 4. I just did them. And so that tells me that, it's not going to happen that K1 and K2 are 0, because if it did, then that's actually just covered in previous cases. So that tells me that K1 and K2, both of these guys are at least 1. I don't know anything about K3 though. So K3, I don't put an additional inequality for that. But this is great. This actually is great. This makes me very happy. Why? Because now if the V's if the V straddles the A's and the V's, if I pump an extra V, right? So what happens if I pump an extra V? So if I have I is equal to 2, then I have W2 is, I have my A's. Then I have the first, right? The first V. So that's this guy. So this guy is the first V. And then I pump an extra V, right? So I have an extra V right after. So then I have A and then B. I have K1As and K2Bs. And then, I have stuff on the right. And then, here I just have A's. But then I have more stuff. I have B's. And then eventually I have C's. I don't even have to make an argument about the length of anything. I can just immediately say this is not an L, right? Why? Because this thing is a pattern mismatch, right? It's now the string does not look like something like A star, B star, C star, right? The string looks something like uh, A star, B star, A star, B star, C star, right? So I just where the number like the A's here, the reason why I argue that K1, K2 is at least one is now here I have at least one A, at least one B, at least one A, at least one B. So I definitely have a break in the pattern that I have to have just A's and then just B's and then just C's. So that's why I get a pattern mismatch. And so I can immediately say that's not an L. And notice that's exactly what's going to happen in all the other three other cases, right? So for case Y, if I pump up, I'm going to get another pattern mismatch. The same thing for the B's and C's for V and Y, right? So then what I can say, right, this was my existential move. Then what I can say for cases 7, 8, 9, I can just say same as case 6. Okay, so same as case 6. And now I have definitely covered all cases. Just try to quickly convince yourself of that. But this actually completes the proof. So I can put a nice box here. And I can finish this example. So in general, the big takeaway here is just make sure to consider all cases. And you can the easiest way to do that is by visualizing how you can shift the VXY part of the decomposition of the string W. Okay. I think an obvious question that you will have is, can you do this in the assignment? Yes, you can do this in the assignment. We're not going to just ask you to regurgitate exactly the same steps. But if you say that a case is the same when it's not, then that's wrong and we take off marks. Okay, so that's the sort of deal that we're making is it's understandable to sort of say same as case 1 when it truly is same as case 1. But if there's any kind of difference, like if there's any kind of difference in terms of the pump, or the fact that the cases they're not really the same, right? So it's not just like a replacement, a homomorphism on the identity of the V and the Y, right? So if it's actually like a different case, then you can't say that it's the same as a previous case, okay? So I think that's a pretty fair compromise. And so hopefully that means that you won't have too many extra pages in your assignment solution. Okay, so I think that does it for these sets of videos. Hopefully I'll get to see you in person next week. And yeah, like I said, next week I'll probably be doing sort of classification. So language classification. So determining, is something regular, not regular, but context-free, or not context-free. So I'll do that, and I'll also start doing some examples of Turing machines. Okay, so yeah, I hope this was helpful, and I'm looking forward to seeing you next time.